Hi, I'm Dacia Cipher, and this is my YouTube channel, Statistics for Nursing Research. This video is going to present how to assess and impute missing data in common health and nursing related data sets using examples in the 4th edition of the Grove and Cipher textbook. There are so many common reasons for missing data. Some are here, where you see that participants can easily be lost to follow-up in longitudinal studies. There may be a failure of instrumentation where the researcher just cannot get a reading, and that creates missing data, mistakes, omissions by the research staff, or the participants simply refusing to respond. Generally, we like to separate two important concepts in missing data: the extent of missing data and the pattern of missing data. Surprisingly, researchers generally agree that what troubles them the most isn't the extent of the missing data, it's the pattern. The extent is how much of the data are missing, generally expressed as a percentage. But the pattern is addressing something else. It's addressing whether the missing cases are differing in some important way from the cells where there are values present. A clear pattern of missing data is an indicator that the remaining data set is biased in some way, and that is a challenge. To determine the extent of the missing data, it's pretty simple arithmetic. You would sum the number of missing cells, and you would divide by the total number of cells, missing or non-missing, in the data set. And I'm going to show you how to do that. When assessing the pattern of missing data, we generally think of patterns as one of two categories: random patterns or non-random patterns. Random patterns are when the probability of a missing cell is like the flip of a coin. It's random. There's no apparent explanation or pattern with those missing data. That would be the most desirable occurrence of missing data, as opposed to non-random patterns, where you are identifying a pattern that can either be partially in the data set or throughout the data set. This is a continuum. Non-random patterns can be thought of as a continuum from a little bit of a pattern to pervasive throughout every variable in the data set. When you find these non-random patterns and you don't address them in your analyses, that can very completely, seriously distort the internal and external validity of the findings. So you have to be very thorough in assessing and for finding any evidence of those patterns. So we have these are the main, most common methods of missing data imputation, otherwise known as estimation. Now, a common one that the researcher may or not even realize that she is doing is list-wise deletion, where if a cell happens to be missing in a participant's row of data, the researcher, when analyzing the data, completely deletes it. That row gets deleted from the analyses. That is list-wise deletion. Pairwise is similar to list-wise. Pairwise is when some of the participants' data are retained for certain analyses where the data are complete, but for a participant's variable values that are missing, like paired statistics like a Pearson correlation or a paired samples t-test, those data would be missing from the analyses. Now, This is never recommended because statistical power is such an important part of statistical analyses. And if you have a small sample, practicing listwise and pairwise deletion makes your small sample even smaller, which affects your power. Never recommended. The other reason this is not a good idea is that if your data do have a pattern of missing data, then by deleting the rows that contain missing data, you are further biasing your eventual inferential statistics. Next would be mean and median replacement. Now, this would be for missing cells for one variable. The researcher would compute the mean for that variable and insert the mean for each of the missing cells for a given variable. Same thing with the median, except you would compute the median for the variable and insert the median for each of those cells. So the problem with median and mean replacement is that when means and medians are inserted into missing cells, they are the same value each and every time for each and every missing cell. So when you are inserting the same value in every missing cell, what happens is the variance of that imputed variable is artificially lowered. Consequently, that's going to affect your subsequent inferential statistic. If your variance is artificially low, your analyses are at risk for a type 1 error. So that is very problematic. The next method of missing data imputation would be regression, where regression, multiple regression, is used by taking the non-missing data and using the non-missing data as the predictors and the values of missing data as the dependent variables. Again, along with the mean and the median replacement, the regression method is problematic because it artificially lowers the variances of those imputed variables. So artificially lowered variances are a problem with the mean, the median, and regression approaches. So a major improvement in missing data imputation would be the method called expectation maximization. Now, this is an iterative process. It begins with correlations among the variables in the data set. And then this method will subsequently use a type of regression called maximum likelihood estimation. And it will iteratively fill in the missing values and adjust the imputed values so that realistic estimates of variance are obtained. That's why it's iterative. It is reevaluating the variances in the iterations so that there are no artificially low variances. That is a major improvement. Finally, we have multiple imputation, probably the most comprehensive missing data imputation approach, because this imputation method also uses that maximum likelihood estimation to iteratively impute missing values. However, it creates multiple data sets. So whereas expectation maximization creates one data set, multiple imputation involves the creation of 3, 4, 5 completely different data sets, all containing possible imputed values. So you have, if you decide to create 5 data sets, you have 5 possible data sets. So you have ranges of values. And then what the researcher will do is use statistical software to compute their planned inferential statistics on each of the new data sets. And the software will combine the results and yield a composite as the final estimate. So like expectation maximization, realistic estimates of variance are obtained, and we don't have to worry about those artificially low variances. Now, I will say that when I am working with a data set where I have identified non-random patterns of missingness, I will use multiple imputation instead of expectation maximization, because I want to create multiple possibilities and multiple imputations so that I do have ranges. Because when we have those non-random patterns, it's important to consider more possibilities rather than less. However, when I have evidence that my data are missing completely at random, I will use expectation maximization and just use the one imputed data set. When reporting missing data in a manuscript, it is important to report the extent of the missing data and also the Little's test. The Little's test is a type of chi-square that is said to assess MCAR, missing completely at random patterns. So if you have a non-significant Little's test, that would indicate that any missing data that you have are random in nature. If you have a significant Little's test, then that means that test has detected some kind of non-random pattern in the data. Finally, you would want to report the imputation method that you used. Let's take a look at a data set here. This is a hypothetical data set where I deliberately created missing data here. This is from a study by Cipher and Urban in 2022, where we studied RN to BSN nursing students who recently discontinued their program. And we assessed them for a number of variables, but the four in this particular example are age at enrollment, GPA, feelings or ratings of stress at discontinuation, and ratings of hopefulness at discontinuation. So we are working in SPSS, but of course, all major statistical software packages are able to do what I'm going to demonstrate here. So let's get started. We are going to assess the extent and the pattern of the missing data. Let's go to Analyze, Missing Value Analysis, move over the four study variables to the right in the quantitative area, and then check EM. Then click on Patterns and click Tabulated Cases, grouped by missing value patterns. Click Continue, and then click on Descriptives, and be sure that univariate statistics is checked here, and then check t-tests with groups formed by indicator variables. Continue and OK. Now, from here, you're going to have a lot of output. And so we'll go through each table. The first table that you see is a simple descriptive statistics table, but it has some very important information here. You have the four variables with the first column. It's the number of non-missing cases per variable. Then you have means, standard deviations, and here you have the number of missing cells per variable. Notice that age has no missing data. You have 3 missing values for GPA, 3 missing for stress, and 4 missing for hopefulness. And then this was turned into a percentage here. You would use this table to calculate the extent of missing data. You would add this column, the missing count, up 3 plus 3 plus 4, and divide by the total number of cells in the data sets. The total number of missing and non-missing cells in the data set would be 20, 20, 20. That would be 80. So 10 divided by 80 equals 12.5%. So the extent of our missing data is 12.5%. Now, in terms of imputation, generally researchers consider that if you have your extent of missing data is less than 5%, that it almost doesn't matter what your missing data imputation approach is. Your eventual inferential statistics will be about the same. Certainly at an extent of 12.5, I'm going to take my data imputation more seriously than that because it is well above 5%. And let's just also notice these last two columns, number of extremes. SPSS is telling me that for the variable age, we have a extreme value in the high range. So when looking at the actual data set, that outlier is actually a value of 68 years old. No low outliers and no outliers at all for the other three variables. Let's look at the next two tables. The next two tables contain means and standard deviations. Now the first row labeled all values, that those first rows here and here display the means and standard deviations as computed in the data set, excluding the missing values. But the second row labeled EM, which is short for expectation maximization, that those two rows, EM here and here, display the means and standard deviations if the EM method were used to impute all of the missing values. Now notice how close the means and standard deviations are to the original, but they're a little different in some cases, as you can see there. Let's look at the next table. Now, this is a dense table of t-test results. And what this table is showing you is it is dividing, it's sort of like a cross tabulation table of study variables in rows and study variables in the columns. And what this table is doing is it is computing independent samples t-tests where the independent variable is two groups, missing versus present. And then the study variable is the dependent variable. So the dependent variables are in the columns and the independent variables are in the rows. So present versus missing GPAs on age, and then it's blank for GPA, and then stress and hopefulness. Same thing for stress, same thing for hopefulness. There is no row for age because there are no missing data for age. Okay, for example, take a look at hopefulness here. The mean age for participants that had non-missing or present values for hopefulness is 37.25. And the mean age for participants that had missing values for hopefulness is 41. If the t-test were significant, it would indicate that a pattern of missing data would be present here where the older participants were less likely to provide hopefulness ratings for whatever reason than the younger participants. So we'd be comparing 37.25 versus 41. However, as you can see, the t-test is only negative 0.6. This is clearly not a significant t. So there's no evidence of an actual pattern here. In fact, if you repeated this and looked at each of these pairs of means in this table, all of these t-values are very low and none of them are significant. Let's go to the next table. Okay, so this table is a very rudimentary visual that is attempting to give you an idea of any patterns that might exist, where the table is displaying X's where there's a possibility of a pattern. Now, this column for age here, this is blank because there are no missing data for age. But these, the columns for GPA, stress, hopefulness, if they have X's on the same row, there may be evidence that there's a pattern here. So for example, for GPA and stress, you have two X's together. And what this table is telling us is that there are 3 instances where participants were missing pairs of GPA and stress values. Now what this row is telling us is that there are 13 participants who had complete sets of data, no missing data. Okay, so the next table, the EM means table, this table is giving us the same information that we had up above with the 2 rows, But this table only contains the means for each variable if we used expectation maximization to impute missing data. But the additional piece of information that we haven't seen before would be the results of the Little's test. Now, remember, a Little's test is a type of chi-square test, and it is detecting whether the data are, quote, missing completely at random. This chi-square at 3.313 is not significant at a p-value of 0.652. Remember that the statistic is testing the assumption that the data are missing completely at random. So if the result is not significant, the researcher assumes that the data are missing at random. Particularly, we would say missing completely at random, even though we want to be careful about that. And the researcher can proceed with missing data imputation with the least probable impact on internal and external validity of the analyses. But however, if the result is significant, that is, if the p-value is less than 0.05, then the researcher needs to assume that there is some evidence of non-random pattern or patterns of missing data. If you find as a researcher that you have a significant Little's test result, I highly recommend that you work with a statistician, because imputation for data with non-random patterns can get very complex, and I highly recommend getting assistance. However, here it is a non-significant result. So basically, any pattern of missing data we had in our example data set, it has not been detected by this Little's test and/or is not impactful enough to be detected. So we move forward, assuming that the patterns are random. Okay, so with that, let me demonstrate how, at this point, now that we've assessed the extent and pattern of missing data, then let's perform expectation maximization data imputation. We're going to go back into the menu we were in before, missing value analysis. We're going to click on EM here, and then save completed data. And then you'll want to name the data set something that means something with no spaces, and click continue and OK. And what SPSS will do is it will create a new data set. And as you can see here, there are no longer any missing values in this data set. SPSS used that iterative EM method to fill in and estimate the missing cells with no artificially lowered variances. So from here, it's that easy. We can now move forward with our planned inferential statistics. And don't forget to, if you did use this imputation method, you would just want to be sure to report it in your manuscript. All right, thank you for watching.